Hi everyone. Welcome to this talk about scaling compute workloads in the cloud. First of all, thanks for the invitation to this event. Very happy to give this talk. My name is Ricardo. I'm a computing engineer at CERN. I'll cover a couple of topics that have been pretty relevant in the last years at CERN and try to give some feedback of our experiences. So a bit about me. I'm a computing engineer in the CERN cloud team. I focus mostly on containers, Kubernetes, and networking. In the recent months or a couple of years, I've been also focusing on GPUs and other accelerators and machine learning and making sure that these workloads run properly in our infrastructure. Previous to this, I worked a lot in storage systems and in the computing grid that is an important fraction of the computing farms we have available for our physicists. I leave here my contacts. Feel free to reach out if you have any questions or comments about what I'm presenting here. I'm glad to discuss more. So, bit about CERN. I'm sure everyone kind of knows what CERN is, but we are the European Organization for Nuclear Research. We are located in Geneva, and we are the biggest particle physics laboratory in the world. We try to have some experiments that help us understand, do some fundamental research that help us understand more about the nature of the universe. The biggest experiment we have today is the Large Hadron Collider. It's a 27-kilometer particle accelerator where we accelerate protons, two beams of protons, one clockwise, one counterclockwise, to very close to the speed of light, very high energies, and we make them collide at specific points where we built these large experiments, which are pictured here: ALICE, CMS, LHCb, and ATLAS. To have an idea of the size of the accelerator, you have the Geneva Airport here on the bottom right. The accelerator is actually 100 meters underground, and it's both in France and Switzerland. The border passes in between. So this is a picture of the accelerator in the tunnel, 100 meters underground. These are the magnets. These are superconducting magnets, and to reach this state, we cool them down to 1.7 Kelvin, which is very close to the absolute zero. This allows us to be able to reach these high energies. So the protons are accelerated by these magnets, and then we make them collide in large caverns that are also in the ground, where we built these very large experiments. This is the CMS, or compact muon solenoid. It's a particle detector that weighs 14 tons. The cavern is 40 meters by 40 meters, and you have the humans there for an idea of the scale. So the protons collide right in the middle here, and the detector acts like a gigantic camera, taking something like 40 million pictures a second. What the result of all of this is a lot of data. Each of these detectors generates something like 1 petabyte a second. This is not something we can handle these days. So what we do is we filter immediately this amount of data, trying to get rid of the non-interesting data, and we reduce this to something like 10 gigabytes a second per detector, which is something we can handle. We store all of this, and then we have a large computing farm that allows us to process this data and eventually get to a point where our end users, the physicists, can do their analysis and generate plots like the one on the right, which shows the peak of the Higgs boson back in 2012 from the ATLAS experiment. Our computing farms are this is our main one, which is at CERN. It's our main data center. We used to have two, but we actually consolidated everything in one in Geneva right now. We have something like 300,000 cores available in this data center, lots of storage. We've stored all this data collection. We generate something like 70 petabytes of data every year. We've accumulated until now almost half an exabyte of data, and this will keep growing. We also use magnetic tapes for long-term storage, but of course the popular data is on disks, and the majority of the data is actually on disks. And then we have our computing farm to analyze all of this. The capacity we have in this data center is actually not enough for what we need to process. So over the last 20 years, we've built this large grid of more than 200 centers around the world that we connected with high-speed network links. And the result is that the end user, the physicist, sees this as a gigantic supercomputer, while in reality underneath it's a complex infrastructure with sites connected from all around the world. If you look at the bottom left, you can see some statistics about how many jobs are running. We see sometimes something like 500,000 concurrent jobs running here. And we more than double the capacity thanks to this infrastructure. So it's quite important to us. We see this kind of a precursor to the cloud, kind of more chaotic in its design. The clouds tend to have less sites and probably more well managed, but it's kind of the idea behind it already was here. So why do we want a cloud? Like, if you think, there has to be some motivation. So in this case, I'm separating what's a private cloud and what's a public cloud. So private cloud is what we run internally. So our data center is managed as a private cloud using a software called OpenStack. And what we try to offer and what we offer our users is an API to manage all types of resources. This includes compute, it includes storage, it includes network, all other sorts of computing resources you can think of. This is quite important. It means that no human interaction is involved when people are asking for resources or provisioning these resources. This is the type of experience that comes with the cloud. What this gives us is improved flexibility, because these operations are much faster since the design promotes this, but also provisioning is much faster. What before could involve a ticket and the allocation of physical resources, this kind of infrastructure in most cases offers virtualized resources, or at least a very simple way to provision these resources that means that you can have in seconds what before could take days or even weeks. It also improves the resource usage in the sense that by having this notion of virtualized resources, you can actually put multiple workloads, even from different tenants, in the same physical resources, making much better use of those resources. So this is the highlights of what we see as benefits for a private cloud. There are others. I mentioned here some high-level services like load balancing as a service, firewall as a service, database as a service. There's all sorts of as-a-service offerings, but this is probably less relevant for the talk today. Now, if we look at the public cloud, the same characteristics are offered both in the API and in management of the infrastructure. But as an end user, what we are more interested is in the extras that we get from it. And this involves on-demand usage. So this, when you have a private cloud, you have a limited set of resources and you want to maximize the usage of those resources. When you're using a public cloud, you can create, shrink, or expand the resources you're being used and delete them all, and only pay for what you're using. So this on-demand usage is key. The elasticity is also very important, because you can grow and shrink the resources very quickly. And also this notion of having unlimited resources. This is how we see the cloud, is that an unlimited amount of resources. This is not completely the case, of course, because there's a physical amount of resources behind it, but it's not far from it. I'll mention a bit more later in this talk. The other aspect that is very important is the access to what are usually scarce resources in our infrastructure. Things like accelerators, GPUs, that tend to be quite spiky these days in their usage in most use cases. It's quite interesting to think that you will explore this availability of these accelerators in the public cloud, so that you only pay when you're actually using them. And also other accelerators that you might never have on premises, like TPUs and IPUs and these kind of new accelerators or FPGAs, things like this are also quite interesting to explore the availability of these in the public clouds. So here I show an example of for the GPUs. So if you notice at CERN, we currently have available NVIDIA T4s and V100s. But actually, if you look at the offerings from all the public clouds, the range is much wider. So you can see all the models available here that we've been testing. So this is an example of one single infrastructure where we are, which is hybrid, both on premises and in the public cloud. We are deploying workloads to try to evaluate their efficiency using these different GPU types. This allows us to understand better behavior of the workloads in these different cards and then think what's the best for them. So should we deploy them in the public cloud in the most cost-effective GPU card that we can find in terms of performance price, or should we in the next tender consider buying different type of GPU cards because we have a lot of workloads that can benefit from that specific card. So this is something quite important for us. Now there's a few challenges when using the public cloud, of course. The main thing is that the clouds are very different from each other. They all use different systems. If you're deploying on premises, probably using some kind of open source software like OpenStack, where you have a lot of commonality between deployments, but there are others. And if you look at the public clouds, they're quite different. This means different in the APIs, but also in the compute profiles. You're offered CPU to RAM ratio, and especially like for things like storage, the I/O profiles are also quite different from one to the other. So you need to understand well what you're dealing with. And then if you start looking at things like billing or identity management, then this is really quite different. The other aspect is that it's quite hard to define a workload in a manner that you can easily deploy in all these different clouds. Or it was up to this changes that were brought by containers that we'll talk in a bit. And then the last one is cost management. So these are done differently, of course, from one cloud to the other, especially if you're doing multi-cloud deployments. Aggregating all of this in a single place can be a challenge as well. So what can help to try to solve these issues that we just mentioned? So the first one is simplifying the definition of the workload. So this is where containers, Docker, and other tools made a huge difference in the last couple of years for us. This promise of build once, deploy anywhere, it's really a revolution to the way we do things. The fact that you can define your workload in a specific way, but in a way that you can run on any kind of platform or tool set. It really doesn't matter what you have in the container. You can be handling a Java application, a Python application, some kind of machine learning workload. As long as you wrap this in this well-defined manner and you're a bit careful about some details, you can actually push this container into a repository, share it with your colleagues, and they will be able to take it, run them in the local laptop, or maybe in whatever infrastructure they have available that supports these platforms, this containerized tools. The second aspect is that you can actually version and tag them. This is quite important if you're managing the lifecycle of the application, but it's also important if you're focusing on reproducibility, which is very important for scientific workloads, of course. The fact that we can think that we take a very old software that used to run in a distribution that even doesn't exist any longer, and we containerize it and we deploy it in a more recent distribution in a modern infrastructure is really a huge benefit for our type of activity. So this kind of reproducibility, the fact that you can tag and share easily these workloads is very relevant. The second part is the management of this workload. So if you think about it, you have the workload defined, but if you want to run it at scale, and we're talking about hundreds, thousands, or tens of thousands of parallel jobs running, we need some kind of orchestrator, something that will manage the life cycle of this application. So Kubernetes came as a good option that gained a lot of momentum in this area, and it really became the lingua franca of the cloud. All the major public clouds offer managed services with Kubernetes, which makes them very tempting for us to manage our workloads as well. So there are offerings for public clouds I mentioned, all the main ones, but also different tools to run on your on-premise or self-managed deployments. What it offers you is this API where you define your workload in a declarative manner that includes the requirements in compute, storage, networking, and then the infrastructure will know how to deal with this properly. Of course, the workload is just part of it. You will want to monitor, to check the logs of your workloads. You will also want to manage properly the configuration and deployment of the workload. So there's a very healthy ecosystem of other tools I mentioned here below that we rely on. There are many more that help with this aspect as well. Now, this is the promise. We have these two components that can help us. Now, is this true? Can they really help us? So we took the challenge and we decided to try a very attractive use case that would also show that all this infrastructure is working well. So we took as a use case the Higgs Discovery back in 2012, and we decided to take that software that already was from 2012, the run, but actually the software was much older than that, and try to wrap it in a container and try then to run that in modern infrastructure managed by Kubernetes. This would show the whole purpose of this effort we've been having. So we chose a specific decay of to find the Higgs. And what this involved was basically processing a large data set of 70 terabytes of data composed of 25,000 files. And what we wanted was to process all this data using a very large cluster of tens of thousands of nodes or cores. In this case, we had a limitation in the software, which was the software was quite old, so it was single core. So we could only go up to 25,000 parallel jobs in our cluster. So meaning 25,000 cores maximum in the cluster. So we took this challenge, and the goal was to first try to run this at CERN. So the infrastructure at CERN, we have a Kubernetes service that is running on top of our OpenStack cloud. And then for storage, we use Ceph. So already here we see that the tools that we use underneath are really not that relevant since Kubernetes abstracts the fact that we use Ceph and OpenStack underneath. All we see is a way to define the compute resources, the storage resources we need, and the rest of the system will handle the access to this. And then the deployment was done using a Jupyter notebook. Of course, we couldn't go to 25,000 cores cluster in this case, because we have a production infrastructure and we can't just steal this amount of resources for a demo. So we did it with a lot less, but still we managed to run a very old piece of software in a modern infrastructure, and even see a huge benefit. Even with the small amount of resources we had, we managed to have the full run being 8 hours, while the initial run took something like a day. Now, what we took after was a challenge of, can we do this? We were invited for a conference talk at KubeCon, and we had only a 20-minute slot, so we took as a challenge, can we reduce this in a way that we can do this live during this demo? So in this talk. So we took this and we actually had a collaboration with the Google Cloud going. So what we did here is we took the exact same definition of the workload, but we directed it to the Google Cloud. And in this case, we had a managed cluster in the Google Cloud that had 25,000 cores. We could scale very quickly. We uploaded the data set to a different storage system, in this case, the Google Cloud Storage. Again, this is abstracted, and the submission again was done by Jupyter Notebook. So in this case, we had the maximum amount of resources we could imagine for this. The result was really quite good after a bit of investigation with details I'll mention in a bit. But what we managed to do is that the actual run, the data staging plus the processing actually took less than 5 minutes. And we had something like 10 minutes if you count the introduction to run the demo. Even if you count the full cluster creation plus the pre-pull of the container image, we were under 15 minutes, which is really like huge improvement and shows the potential of this kind of infrastructure. So in the end, what we demoed was the fact that like we could build the plot live as the computation was going. Now, some takeaways of this. The first one is that there are clearly use cases where end users having access to this type of resources will have a huge benefit if they can just redirect their workloads and get their analysis done in a couple of minutes instead of waiting for longer periods in a queue. Of course, not all the workloads match this kind of usage. Other takeaways that on the usage of the cloud were that you still need some knowledge of the infrastructure. This is particularly important in storage for data-intensive workloads. So you need to understand the different profiles that the cloud offer and which one is more adapted to the workloads you want to use. The second takeaway is that unlimited, as I mentioned, can be still limited. Depending where you direct your workloads, you realize that the available resources can vary, especially when you're deploying a large amount of resources like we were doing here. So you will get a sense of this while as you use more the cloud service you chose. You will see that some regions tend to have more availability than others. The last one is that when we start looking at cost, there are also important details. So the full run with normal instances we were doing costs something like $260, which is already quite good. As we managed to scale this much, we end up using the resources for a very short period, so the price is quite low. But actually, if you start looking into the details, there's the possibility of deploying preemptible or spot instances, which are basically low SLA compute instances that are something like 5 times cheaper. So they are very, very tempting. Also, you should check for the availability of committed or sustained use discounts. This can give you something like 30% savings on the price even of preemptible. So it's all these bits start making for serious savings. What we see is that this kind of activity is not for all the workloads. The workloads that are 24/7 are probably going to be more cost-effective to be run on premises. But for spiky workloads or extra capacity, this is very tempting. Now, where does this take us? This is the important thing. We demonstrated that we have all the technology, all the pieces that we need to do this kind of activity. It's quite important to see like how far can we get this. So we started basically betting on Kubernetes as our common infrastructure layer and starting to deploy a lot of applications on top of it. So we already have things like Jupyter Hub, HDConder, Kubeflow, which is a machine learning platform, Slurm, Rihanna, which is a reproducible analysis platform developed at CERN, Binder, which is used for reproducible builds of containers and analysis as well, and other tools. We started putting them all on top of Kubernetes. And if you think about it, we can think that all of them would run in the same cluster to make the best use of this. But it could also mean have them on multiple clusters. And you can even have the majority of your workloads running on premises. So in this case, in our infrastructure at CERN. And then for some workloads where it makes sense, we direct those workloads to the public cloud. And this is with this possibility of having managed Kubernetes services in all the major clouds, you can think that it's quite easy to move even between the clouds. There are some details I'll mention at the end as well, which are more on the cost side, but technologically we already have this kind of setup. So what I will do now is try to give you a demo of how this works. So I'll start. So I mentioned the reproducible analysis platform we have, but in this demo, I'll actually use this tool called Binder. Binder is basically a way to have a Git repository where you define how your container or your workload should be packaged, and you can version them using a familiar tool like Git. So what I will do, I have my repository here, which is my Binder repository that is here. What I will do quickly is I will just amend the last commit, which was basically an update in the file just to trigger a change in the git commit hash so that it triggers a rebuild because the system will think that there was a change, so it needs a rebuild. So I'll push this into our system. So we got a new commit, which is this one. And then I'll just pass the repo here. I'll put the branch that I'm using. You can actually imagine that different people will use different branches. It's quite flexible in this way. And I'll just do launch. And in here, we'll see that it's waiting for the build to start. It detected there was a new commit here that it never built. So it's triggering the build now of the container. And again, this is running on our Kubernetes cluster. This is quite important. So we can imagine that we are reusing the resources here. So we can see we just started the build of the container. So this is the same cluster where we are running the actual notebooks and where we are running a lot of the other workloads. So I'll just let this build here. And what I will do is I will jump quickly to the Git repository that we have here. And I will click this launch binder. In this case, instead of rebuilding, it's actually trying to launch the master branch. And this has already been built because it's a popular branch to be used. So it's just launching the server. And we can probably see here that it's already, we don't see it here, but I will jump here to the notebook anyway. So the binder, I'll just give some details of what this looks like. In this case, this binder repo is just a Dask application. The definition of the binder modules is in this directory. And then it triggers a notebook that has a bunch of files inside and has this nice way of submitting Dask applications. Dask is a popular framework for distributed processing in Python. So I'll jump to our notebook here. So what I will do here, I'll take the notebook that I was launching before, and this is already here running in my environment, in my notebook environment. And normally this notebook would be run with the Dask client just talking to the notebook server itself. Well, but on the left, you see that I have this Dask interface on my left tab, and I can just drag this, and this is the configuration of the cluster where we are running the compute workloads. So this is again this idea that we can centralize the different compute workloads to be run in the same cluster that then we can auto scale or scale out to the public cloud. So if I run this, I'll first configure the cluster, and then I start doing the computation here. This is the first one. So Dask has this nice way of also exposing how things are progressing. And if I show you here very quickly, you can see that I have some Dask workers that were being created recently, like just now, to run my workloads. Others are terminated because they finished and they are not used anymore. So I already run the first part of the computation. If I go and run the second one, which is a bit heavier, it should also start doing some additional computation. So there we go. So different tasks being run. It's a very silly application, but it gives kind of the idea, like we have all these complex tags that then we can run in a remote cluster. And you can see again that it's terminating the pods that are not being used anymore. So these are the different workers that it's triggering. So one thing that we could try is, for example, here I'm saying the number of workers I want to use. You could say scale the cluster and then just force the number of workers to be 5, let's say. So, and in this case, we would just want to clear the outputs and probably just restart the kernel to be sure. And then if we do this, we already have the cluster there. So we start going, and we should now see a lot more workers being created as we go. So here we go. So we said we want 5 workers. We already got 4 created. So if we took this to the limit and we, for example, went over the available resources for this cluster, what the cluster would do is auto scale, which is one of the big features of Kubernetes. It's when it doesn't have any resources, it tries to autoscale the cluster itself to the maximum we define. So this is something that is very useful. The users can just define the amount of workers they need, and we have quotas, of course, for each user. Now, one additional application that I would like to show is a machine learning platform that we recently started looking at. This is called Kubeflow. And this is quite powerful in the sense that the way it handles notebooks is quite nice, in addition to those things like hyperparameter tuning. But again, this is running in the same cluster that we are running the Jupyter notebooks, which allows us to have this centralized and this consolidation of the usage of the resources and manage this as we wish. So very quickly, I'll do this. There's this tool called Kale. The biggest feature of this application is that you can have a simple notebook defined in the way you see here, and then you enable this, and this defines like tags on each of the cells, and out of these tags, it will actually create a pipeline. And these pipelines can be as complex as you want. So in this case, we are defining a set of parameters for the pipeline, a couple of first steps where you can see that we can introduce dependencies as well. And then we have two different model trainings that again depend on a previous step. You can define if you want a GPU or not. So in this case, we will not use a GPU. And then we can aggregate the results and print them. So this is quite nice. The way this works. I'll just submit this quickly. I can ignore this message. And this will create our pipeline. You can submit directly from the notebook. And again, the pipeline behind, even if you're running the notebook server already in our Kubernetes cluster, the pipeline can use a lot more resources potentially. And it's again running on our same Kubernetes cluster. So this is what we are trying to achieve, is this consolidation where we separate well the different applications that people might be interested in using from the infrastructure itself. And you can see that I already showed like 3 different applications, and we have a lot more that are using the same kind of pattern. So if I again show you what's going on here, you can see what's running on the cluster. So in this case, it's running on my namespace where I have a certain quota. You can see I have some old stuff running, but you can see also that I have this one that just started 11 seconds ago, which is one of the steps in this process. We mentioned that there was this reading data, processing the data, and then finally we start having our 2 models being trained. And eventually we'll have the aggregation. So one thing I can also show quickly while we wait, when you create a notebook, you can specify a custom image, which is quite interesting. Or one thing that would be really nice is, for example, the integration of Binder also with this tool. You can set the resources you want to use, some other details. You can see if you want GPUs and which kind of GPUs, and then you can launch. So in principle, we should be almost done here. You can see one of the model trainings. It's a quite simple example, of course, for this quick demo. You can see one of the examples is done. One of the trainings is done. The other one is about to be. So one other thing that this tool also does, it integrates very well with the rest of the Kubernetes API. So you can even, for example, check a step and then go for details about, for example, the logs of this step. You can see what's happening. So this is quite important for our users to get some feedback on what's going on. And then, for example, in the model evaluation, if you go for the results, you can see here the accuracy of each of the models we've been training. So this is, again, building on the Kubernetes API and offering quite advanced interface to our users. There's other capabilities in this tool that focus on hyperparameter tuning, but I won't have time to demo this today. So going back to my presentation, we come to the end pretty much. So I hope to have given you an overview of what our experiences of using both private and public cloud have been, and what are the key aspects that make them interesting for a place like CERN. There's still a lot of ongoing work, of course, and I would highlight as challenges today for what we are doing. I would say one of them is the egress cost. So if you have experience with using the public cloud, this is public cloud specific. Ingress is very cheap in the sense, or it's actually free in the sense that you can upload as much data as you want, and you won't pay for the inbound data transfer. You will pay for the storage and parking of the data, but you don't pay for the ingress. On the other hand, if you have a workload that generates a lot of data and is running on the public cloud and you need to take it back, then the egress costs are very, very high. And they can take a large chunk of the costs you're having with the public cloud. So there's ways to try to get waivers that you can negotiate with the cloud providers, but the default egress costs are quite important. Then the second one is that if we want this hybrid infrastructure where we scale transparently from an existing cluster on premises to the public cloud, we need some kind of pretty complicated networking setup. And this is something that we are investing also to improve. This is a key aspect. We can have the workloads being submitted to remote clusters, but we also have use cases where we would like to expand an existing cluster to the public cloud. And then the last one is the scheduling of data intensive workloads. If your workloads need a lot of input data, as ours do, you will need some kind of smart system for the scheduling on the different resources you're integrating, be it on premises, of course, which is easier, but also specifically if you are submitting workloads to the public cloud, you have to have a way of either pushing the data there before the workload or submitting the workloads where the data is already. So this is something we've built. We have systems that handle this that we've built over the years, but it's an important aspect to take into account. And with this, I come to the end of my presentation. I hope it was a good overview of some of our experiences. I'm happy to take any questions. And if not, feel free to reach out. I leave my contacts here both. And yeah, feel free to reach out. I'm happy to discuss this with more people and also listen about more about your experiences. Thanks again for the opportunity, and enjoy the rest of the conference.
Thank you, Ricardo. That was an impressive setup, I feel, and we have also some questions here already. So I will start with the first one, which is more related to this huge LHC setup, where I think it was Frank, if I'm not mistaken, he said, yeah, there's a lot of events in this setup of these protons, which is well understood and not really relevant, maybe, or very well known. So that's not really interesting to see. But how can you narrow down and see the interesting event? Because that's kind of a challenge if you have so much noise, so to say, with respect to those things which really interests the scientists.
Yeah. So yeah, thanks. And that's a pretty good question. I'm not sure I know exactly how to answer it because it's pretty complicated physics. What I can explain is how it's done. So when we see all this hardware that we have in the detector, it traces these particles, generates a lot of data. What they do is they have a first high-level trigger, it's called, and this trigger is just a filter that basically is based on hardware these days. In the current runs that we had until now, they are hardware-based, so they are custom-made boards that focus on filtering this background noise that is defined by physics that I don't really completely understand. One interesting bit is that because of the evolution of technology, a lot of this filtering with the same efficiency, we will be able to, in the next runs, move some of it from hardware to software. And this will be GPU-based farms, and maybe some FPGAs as well. But this gives us a lot more flexibility in the way we will do the filtering. So we have a lot more potential to change things dynamically instead of having like custom-made hardware. So this is a big change. Yeah, we basically tune the trigger in the way that we leave as much data as we can actually process. Like if we would say to the physicists, you can keep everything, they would probably say, yeah, we want that, but it's just not possible. So we kind of tune the calibration of the detector so that we keep as much as we can.
Okay, good. Thank you for that answer. I see here in the stage there are some more. Yeah, so the second one I would put forward is, of course, this impressive notebook setup where you seem to have full control also on the pipeline and these kind of things. So James here has asked how technically it's done by Git hooks, or how you trigger, so to say, the resubmission. And then there was also a question of two persons, again, James and Satyam, on the bits and pieces, how this is done with these tags and these headings. So maybe you could elaborate that a little bit more.
Yeah, so the binder setup is really focusing on this, is integrating with Git, and using the Git versioning to understand if I should rebuild the image or if I just use an existing image. Like building images can be a kind of lengthy, like can take quite a while, depending on the setup, of course. But it's quite what the tool does. It's behind it has a tool called repo to Docker, which is basically it does what it says. From a Git repo, you can generate the Docker image, and it's done on demand. So it's not triggered by a hook. In this case, it's really done when a user asks to launch a notebook based on a Git repository, and uses a branch or a tag or just a commit ID that was never built. Then the system will build it, will push it to our Docker image repository or registry, and then the notebook is launched based on that built image. The second user that comes behind already has the image built and will have the notebook being done very fast. What we do as well, we do some tricks, which is for the popular ones, we do this. We do trigger this based on Git hooks, just to build. We do a call that generates the build, and then the popular images are also pre-pulled on the nodes, because once you have it built and in the registry, it can also take a time to pull the Docker image to the worker nodes that are running the notebooks. So we have a list of pre-pulled images that are always available, so that our users have a really nice experience where everything is super fast.
Very good. Yeah, it's quite a lot of technology behind the scenes. I mean, we have been experimenting here also a little bit, but I mean, it's by far not the same scale.
Yeah, well, but the mechanisms are all there.
Yeah. I mean, I think especially for our group here, we are getting slowly there to make it more use of the newer technologies. But yeah, we are learning even from you, I think, awesome. As we speak here. So I have one last question, maybe, there's two eventually. Let's see, we still have 2 minutes. So one is again from Frank, I think, regarding the machine learning techniques. Of course, we have a lot of talking nowadays about deep learning, artificial intelligence, and those are hugely benefiting of the parallelism offered by GPUs. So can you give us a rough idea on how this scales at CERN? You once said you have unlimited resources. I suppose for GPU that might not be the case, but so how is it? How many jobs are already benefiting from GPUs, and how do you see that in the future? Are we close to commodity, or will it be also always a scarce resource?
Yeah, so this is a super hot topic internally. Like we don't really have unlimited resources on premises, definitely not. Like the public cloud, we see it as unlimited, and this is where we try to go for these scarce resources. The usage of GPUs is ramping up, that's for sure, pushed by a lot by this machine learning, but also by this conversion of the triggers from hardware to GPU-based solutions. One thing, it's quite hard to trace these days. One thing, the reason I showed this machine learning platform we deployed, one of the main reasons to focus on this is that we have a lot of, like CERN is pretty big, so we have a lot of groups doing different things in different ways, and it's very hard to track all of this and consolidate the usage. So we are trying to get a system that people are happy enough with it, and I think we are getting there, that they will see the benefit of just using this centralized system, and this will allow us to do a much better management of the resources. What we see is that the usage of GPU depends really a lot on your workloads. And even, it's not even the usage of GPUs, it's the type of GPU you will use. A lot of the workloads require things like double precision performance, and you will need like the top enterprise expensive cards. And in other cases, you can get away with like cheaper cards, and you might just stay in a corner or something. So we are also trying to onboard all these GPU workloads, run them on all our available hardware, both on premises and outside, and then give feedback to the user saying, okay, the best for you is this GPU.
So you give suggestions.
And we give a lot of feedback in it. It will also help us, because these things are moving so fast, for the next tender, when we buy the next set of GPUs, to see how much and which kind. It's also very important. It's not only like how many GPUs, it's what type of GPUs should we be focusing on. I can't say that I know like what's the fraction, but there's so much happening that I don't think there's a way back. There will be a place for GPUs, like a large fraction for computation will move to GPUs in the next couple of years.
I mean, it's a little bit similar here. Again, not the same scale, but electron microscopy, or cryo-EM, these kind of things, imaging in general. I mean, they are relying on these analyses.
There is one like very big use case for us, which is to generate simulation data, and we are seeing improvements of like 1,000 times by using GPUs. This is like a dream. So I'm sure there will be a place for this.
Okay, very good, Ricardo. Thanks again for your time. So usually now it's the time for the applause, so I will do it here. Only one, at least. Thanks a lot for doing all the efforts and preparing the presentation.
Pleasure.
Being here for the questions. And I think exciting futures ahead for all of us busy in either physics or life sciences with the cloud. Good. Thanks a lot.
Thanks for the invitation.